Welcome to a new physics class. Today we'll continue our study of the Doppler effect. Okay, so last week we looked at the acoustic Doppler effect. Okay, the acoustic Doppler effect. Okay, that was the change of the frequency of the heard sound when the source of sound or the detector, the microphone or the ear, are moving. Okay, so sound waves. And the formulas given in the booklet are for the moving source and the moving observer, but we were able to show that you can have both a moving source and a moving observer. So moving source f prime is f v over v plus or minus vs, the speed of the source. Okay, and moving observer f times v plus or minus the speed of the observer over the speed of sound. So here in these formulas, v is about 343 meters per second, speed of sound in air. Okay, and the sign the plus or minus signs are chosen in such a way that the frequency increases when the source or detector are getting closer. That's something we have to remember because we have to pick the correct sign when using the formulas from the booklet. Okay, and when both are moving, we simply multiply the two factors and we get something like The new frequency is the old frequency when both the source and the detector are at rest, times V plus or minus VO over V plus or minus Vs. Okay, and this is a very important formula because we'll start from this formula when we will talk about the relativistic Doppler effect. Okay, which is our next topic. Now, in the booklet, we have a third formula. In the booklet, we have a third formula right here, delta F over F equals delta lambda over lambda. It's approximately equal to V over C. Okay. You got to be very careful because the V in this formula is not the same as the V in the previous two formulas. It's something completely different. And we'll see more right now. Okay, so the relativistic Doppler effect okay, works with electromagnetic waves. That is light. And this is how it shows up in the textbook. The Doppler effect with light. In the textbook, they give a very, very brief discussion that ends with the formula in the booklet. And I believe this effect deserves more time and effort from our part to fully understand it. Okay, so what is the difference between light and sound? What is the difference between light and sound? Why do we need two different Doppler effects? Okay, so first, sound needs a medium in order to propagate. Sound needs a medium that is air, for example, in order to propagate. Okay? We work in the reference frame in which the air is at rest, does not move. So there is such a reference frame. Light does not need a medium. a medium, okay, in order to propagate. This is very surprising because all the other waves, uh, seismic waves, elastic waves, okay, they all need a medium, an elastic medium in order to propagate. And this was also supposed to be the case for light. Uh, the hypothetical medium ether was proven not to exist by Einstein. So Einstein, with the theory of special relativity, Einstein in the theory of special relativity has shown that the ether does not exist. And because of this, any reference frame is as good as another. And I will add inertial reference frame. Any inertial reference frame is as good as another. Okay, what's the meaning of inertial? That means moving with constant velocity. Moving with constant velocity. Okay. Well, that means we cannot talk about the speed of the source relative to air. So instead of speed of source relative to air, and the speed of the detector relative to air, so instead of talking about the speed of the source of sound relative to air and the speed of the detector of sound relative to air, we have to use the speed of source relative to the detector. Okay, this is what the theory of special relativity tells us, that only the relative velocity matters. So special relativity. Only the relative velocity matters. Matters. Okay. So that's one big difference between the acoustic Doppler effect and the relativistic Doppler effect. We have to make this relative velocity show up. And another important difference is that the speed of light is much, much greater than the speed of sound. Speed of sound, 343 meters per second. Speed of light, 3.00 times 10 to the 8th meters per second. Much, much bigger. Okay. So now we'll look at one situation. Okay, the source and the detector are moving let's see, towards each other or away from each other. Doesn't matter. Well, maybe we should do both situations. Okay. So source of light may be a star, yeah? And detector, okay, radio telescope or something. Are moving towards each other. This will be case one. Okay, so how do we write the formula? They are moving towards each other. That means the new frequency has to be greater than the frequency when both are at rest. So in the formula, to make the frequency bigger, I will pick a plus sign on top and a minus sign on the bottom. Okay, so I have the source moving with the velocity v source, and I have the detector moving with the velocity v observer. Okay, and also v is very, very big in this formula. Okay, so first of all, I'm gonna have a change of notation. So instead of v, I will call it c, speed of light in vacuum. Yeah, 3.0 times 10 to the 8th meters per second. C. Just so I know, this is a very special speed. The maximum possible speed in the universe. The maximum speed in the universe. Okay, so with this notation, the formula will become the new frequency is the old frequency C plus V observer over C minus V source. I divide up and down by C, the speed of light, and I get 1 plus VO over C over 1 minus Vs over C. Okay. And because the speed of light is so big, these fractions, VO over C and Vs over C, are very small. Okay, which allows me to make some approximations. So the first approximation I will make is, so if x is much, much less than 1, then 1 over 1 minus x is about equal to 1 plus x. Okay. How can we prove this? Well, when x is super small, x squared is about equal to 0, right? Think about if x is 0.001, what is x squared? 0.000001, okay? We can ignore it. Okay, that's the idea. And this approximation is equivalent to this approximation. 1 minus x times 1 plus x is approximately equal to 1. Well, I know what this is. This is 1 minus x squared is approximately equal to 1, which indeed is true because x squared is about 0 and we cancel it. Okay, so if we use this approximation, the formula here becomes f prime is equal to f1 plus v0 over c times 1 plus vs over c. Okay. And now we use another approximation. When we multiply the binomials, okay, if x is much, much less than 1 and y is much, much less than 1, okay, which means xy is about equal to 0. Again, the product, yeah? Then 1 plus x times 1 plus y is about equal to 1 plus x plus y, which we can see by expanding the product of binomials. Yeah, we FOIL. What do we have here? 1 plus y plus x plus xy, okay? And again, the product xy is about 0. We cancel it, and that's what we get. So again, think about this. If x is 0.001 and y is 0.001, what is xy? It is 0.000001, super small, can be ignored. And as a matter of fact, this is what we get when we look at, 1 over 10 to the third. But imagine we divide by the speed of light, that's 10 to the eighth, yeah? So the x and the y in our calculations are much, much smaller than 0.001. Okay, so with this approximation, this product becomes f prime is f times 1 plus v0 over c plus vs over c, which is f times 1 plus v0 plus vs over c. And here what we have is the relative velocity. v0 plus vs is the relative velocity, the relative speed with which the star and the Earth are moving towards each other. Correct? So let me draw a reference frame like this, X, the origin, the source, okay, with the velocity Vs, and the detector with the velocity V detector, okay, and the Vs x, the x component is what? It is Vs, right? Positive because it's moving to the right in this diagram. And the detector, the x component, is negative Vd, negative because it's moving to the left. And the relative velocity Vs minus Vd, yeah, has a x component, yeah, Vsx minus V dx, which is, as you can tell, Vs plus Vd. And I changed notation. I wrote T instead of O, but it's the same thing, yeah? Detector, observer. So this is what we have here, the relative speed. Okay, and now, unfortunately, we make another change of notation. Change of notation. Okay, so VO plus Vs becomes V. Okay, the relative speed. The relative speed. The relative speed of approach. Because they are getting closer, yeah? And the formula becomes f prime is equal to f times 1 plus v over c. And this is the v in the formula in the booklet. So this v is no longer the speed of sound as it was in the first two formulas. Okay. And now we have to prove that delta f over f is equal to delta lambda over lambda is equal to v over c. But before we do this, let's also analyze the second case when the source of light and the detector are moving away from each other. Okay, as you can tell here, the frequency increases, yeah? They're getting closer. They are getting closer, and f prime is greater than f. I multiply by something greater than 1. Okay, case 2, they are moving away from each other. Source of light and observer are moving away from each other. Okay, that will mean that f prime is less than f. Now, again, I start with the formula from the acoustic Doppler effect. f prime is f, and because the frequency will decrease, here on top I have to pick a minus sign, v minus vo, and on the bottom of the fraction I have to pick a plus sign, v plus v source. Okay. With the change in notation becomes okay, change in notation v becomes c, and the formula 3.0 times 10 to the 8th meters per second. The formula becomes f prime is equal to f c minus v0 over c plus vs, which is f times 1 minus v0 over c over 1 plus vs over c, the speed of the source over the speed of light. And I do the same approximations. So now the source is moving away. The detector is moving away. And the new frequency will be equal to again 1 over 1 when x is much less than 1, 1 over 1 minus x will be about equal, 1 over 1 plus x will be about equal to 1 minus x. This is the approximation I'm using. I change this to 1 over 1 plus vs over c into 1 minus vs over c. So the new frequency will be the frequency when both the star and the telescope are at rest times 1 minus v0 over c times 1 minus vs over c. Okay, these fractions are super small. And now I use another approximation because I multiply the super small quantities, right? This could be my, so this was my x here. Now this is my x and this is my y, yeah? And when x is less than, much less than 1, and y is much less than 1, 1 minus x times 1 minus y is about equal to 1 minus x minus y. Again, if I expand, I FOIL, what do I get? I get 1 minus y minus x plus xy, but this is about 0. So it goes away, and that's my proof. So the new frequency will be equal to f times 1 minus V0 over S minus Vs over, excuse me, C, not S, C. Okay. F prime is F1 minus V observer over speed of light minus V source over speed of light, which is F times 1 minus V observer plus V source over C. Okay, and again, I have the change in notation. Okay, VO plus VS is the relative speed, with which the star and Earth are moving away from each other. Okay. And again, we have that unfortunate change of notation. Okay, VO plus VS becomes V, the relative speed of okay, what's the opposite of approach? Relative speed of getting away from each other. Okay, and the formula becomes F prime is F1 minus V over C. Okay, they are getting farther away. That means the new frequency is less than the frequency when both are at rest. Okay. Now, suppose you look at the electromagnetic spectrum. Okay, and you have you basically have the rainbow in the middle, visible light, yeah, red, orange, yellow, green, blue. Okay, um, indigo, violet, ultraviolet, and so forth, infrared, so forth. Okay, and suppose we have a frequency somewhere in the middle of the visible light, yeah? If the frequency goes towards the red, okay, if f prime is less than f, we say that light is red shifted. Okay, and this happens when they are moving away from each other. The star is moving away from Earth. And if the frequency gets towards blue, okay, that means f prime is greater than f. We say that light is blue shifted. Okay, which means the star is moving closer to Earth. Well, experimental astronomy shows that most stars, most galaxies are moving away from Earth. The universe is expanding. That's an important result we got using the relativistic Doppler effect. Okay, so now I'm gonna combine these two formulas into one. So f prime is f times 1 plus or minus v over c, when the sign, again, plus means getting closer, minus means getting farther apart. Getting farther apart. Apart. I think only one p. Okay, so f prime is f plus or minus f times v over c. Okay, which means f prime minus f is equal to plus or minus f v over c. F prime minus f over f is plus or minus v over c. Okay, and now I take the absolute value on both sides, and as a result, I end up with the formula in the book. Delta f over f is equal to v over c, where of course I have to remember that delta f is absolute value of f prime minus f, yeah, and and f prime is greater than f when they are getting closer. F prime is less than f when they are moving farther apart. This is a strange notation, okay, because usually delta means new minus old without the absolute value bars. Okay. How do we end up with the other formula that uses the wavelengths? So basically, I have to prove that delta f over f is equal to delta lambda over lambda. Now again, delta lambda by definition will be the absolute value of lambda prime minus lambda. And you got to realize if f prime is greater than f, then lambda prime is less than lambda. If f prime is less than f, then lambda prime is greater than lambda. So if the frequency increases, the wavelength must decrease the other way. So I cannot have a positive f prime minus f and a positive lambda prime minus lambda at the same time. Yeah, I cannot have positive f prime minus f and positive lambda prime minus lambda at the same time, which is the reason why in the definitions of delta f and delta lambda, I need to include the absolute value bars. Here, the formula in the booklet is indeed a little bit confusing. Okay, in any case, how do we prove it? Well, this is what we know. We know that the frequency times the wavelength is the speed of the wave, in this case, the speed of light in a vacuum. Yeah, that's the reason why if one increases, the other must decrease. Yeah, f prime lambda prime is same speed of light c. The speed of light does not change from one inertial reference frame to another. Okay, that's another important conclusion from the theory of special relativity. Okay. So we can say lambda prime is c over f prime. It is c over f one plus or minus v over c. Which is c over f. And again, I use the approximation because v over c is super small. I get 1 minus or plus v over c. But this is lambda, right? C over f. So lambda prime is lambda 1 minus plus v over c. Lambda minus plus lambda v over c, which means lambda prime minus lambda is minus or plus lambda v over c. Lambda prime minus lambda over lambda is minus or plus v over c. And again, I take the absolute value on both sides. And with the notation delta lambda is absolute value of lambda prime minus lambda, I end up with delta lambda over lambda is equal to v over c, the second part of the formula in the booklet. So in the booklet, as you can see, the two formulas are brought together. Okay, in the booklet, this is what we see. Delta F over F is equal to delta lambda over lambda is about equal to V over C. Okay. What are important applications? We talked about this last time. In meteorology, you can find the velocity of the clouds, the speed of the clouds. In astronomy, you can find the speed of the stars, of the galaxies, and also police officers use radar to find the speed of the moving cars. But in a situation like this, the Doppler effect applies twice. Okay, and there's a problem I want to discuss. Okay, next. When finding the speed of a moving object, by reflecting a wave on this object, the Doppler effect applies twice. And this is mentioned in the textbook. Okay, the applications right here. Okay. In order to use the Doppler equations, we must recognize that the moving object, first of all, behaves as a moving observer, and then when it reflects the microwaves, behaves as a moving source. This means the equation delta F is about FV over C is adapted to become delta F is about equal to 2 times F times V over C. Okay, which is a good time to write a homework assignment. So homework, read. Okay, 9.5 again. And answer. There's a problem at the end of the chapter. number 13 on page 390. Okay. I'm gonna look at this problem. Okay. Problem number 6 from the higher level paper 2 from this year, May 2022. Okay. An experiment to investigate simple harmonic motion consists of a mass oscillating at the end of a vertical spring. So the moving object is this mass. And we have a motion sensor. The mass oscillates vertically. Okay. And we'll skip to the last question. The motion sensor operates by detecting the sound waves reflected from the base of the mass. The sensor compares the frequency detected with the frequency emitted when the signal returns. Okay, so this is the Doppler effect showing up twice. The sound frequency emitted by the sensor is 35 kilohertz. The speed of sound is 340 meters per second. Determine the maximum frequency change detected by the sensor for test number 2, the frequency change. So, okay, when something moves, reflects a wave, you look for a frequency change. That is clearly the Doppler effect. Okay, now, and this is for 4 mark points. The first mark point is simply from getting the maximum speed from the graph. And this is for, one more time, this is for sensor for test 2. Test 2. So I look at the graph. Okay, test 2 is this dashed line. Okay, what is the maximum speed? Maximum speed for test 2. Okay, well, look, I have the graph. 5 divisions between 8 and 10. Yeah, 5 divisions between 8 and 10. And the maximum speed shows up somewhere in the middle of this division. Yeah. What is the value here? What is the value here? Okay, if you read this number correctly, you get 1 mark point. Okay, so first of all, how big is 1 division? How big is one division? Well, 10 minus 8 divided by 5. I have 5 divisions. This is 2 divided by 5. This is 0.4. Okay, so this is 8.4, 8.8, 9.2, 9.6, and 10. Okay, and I'm right in between 9.2 and 9.6. So, right, I need to find the average value because I'm in between 9.2 plus 9.6 divided by 2. That's exactly 9.4. So 9.4 meters per second, that's the maximum speed. I read this number from the graph. I get 1 mark point. Okay, and then back to the problem. Okay, the sound frequency emitted by the sensor is 35 kilohertz. So the source emits with the frequency 35 kilohertz. Okay, and the object, okay, let's say it moves closer to the sensor with a speed of 9.4 meters per second. This will be the observer, yeah? Step 1, the moving object is the observer. And what frequency will it observe? Well, f prime is, again, back to the booklet, the formula for a moving observer. Moving observer, so will be f times v plus v observer over v. Okay, so this will be v observer. Okay, and we plug in the numbers. We are told that the speed of sound is 340 meters per second, so 35 kilohertz. Okay, 340 plus 9.4 over 340. Okay, calculator. 349.4 divided by 340 times 35, and I get 35.97 rounded. Okay, well, guess what? This is rounded to 36 kilohertz. Okay, and now I have to realize that there is a step 2. Okay, okay, the object moves, but now this is the speed of the source because the wave reflects off, yeah, the moving object. Step 2, the moving object is the source. The waves reflect off it. The waves reflect off it. Okay. And the ultrasound or microwave sensor is the detector. Okay, so now we have to use the formula for a moving source. Okay, moving source. F prime. I'm gonna say F double prime because F prime is what we calculated above. Is F times V over V minus V source. The source is moving and it's moving towards the detector. The frequency must get bigger. I have a minus sign. Okay, so now I plug in the numbers. 36 kilohertz, okay, times 340 over 340 minus 9.4. Okay, what is this? Calculator. 340 minus 9.4 equals 1 over x times 340 times 36, 37.02, which is about 37 kilohertz. Okay, so what is the maximum frequency change? The maximum frequency change 37 kilohertz minus 35 kilohertz is equal to 2 kilohertz. which is what you need to get the fourth mark point. So we have applied the Doppler effect twice to relate the change in frequency when the reflected wave comes back, okay, to the speed of the moving object. That's how the police officer can figure out the speed of your car. So hopefully you will drive within the maximum speed limit and avoid any tickets. Okay. One more thing I wanted to do today to assign you another problem with the Doppler effect that was given in the November 2017 exam session. Okay. Okay. So sea waves move towards the beach at a constant speed of 2 meters per second. They arrive at the beach with a frequency of 0.10 hertz. A girl on a surfboard is moving in the sea at right angles to the wave fronts. She observes that the surfboard crosses the wave fronts with a frequency of 0.40 hertz. What is the speed of the surfboard and what is the direction of motion of the surfboard relative to the beach? Okay, so okay, we have a frequency of the waves arriving at the beach. We have a frequency of the waves noticed by the moving observer, yeah. And we have to figure out the speed and the direction of motion. And these are the 4 choices. Okay, so this problem is also added to your homework. We'll talk about it next time. Okay, thank you very much for your attention and good luck.